please put your hands together for Senior Research Engineer Howard Herzog. Welcome. Thank you.
Good morning, everyone. It's a pleasure to be here. I thank Climeworks for inviting me to speak today. And I was going to say, I was actually planning to come to the first Direct Air Capture Summit that was be held in 2020. Had my plane tickets and everything ready to go, and then COVID happened. So it's 3 years later, but I'm happy to be here and talk to you today. Do I have? Oops. Okay. So what I'm going to talk about is trying to get up to scale. CDR, carbon dioxide removal, there's quite a buzz about it, as we all know. There's conventional wisdom, which I believe is that you cannot get to net zero without having significant amounts of carbon dioxide removal. The good news is there's a lot of options for doing this. The things is also a lot of challenges. Each of these has challenges. Some have different challenges, but they all are challenged. But even just the mitigation technologies of reducing our emissions, just about every one of those mitigation technologies is also challenged. So this is sort of par for the course in this field. So let me start by telling you what I believe the best way to remove CO2 from the air, and the best way to do it is not to release it to the air in the first place. I think that bears repeating. The best way to remove CO2 from the air is not to release it into the air in the first place. So, why do we want carbon dioxide removal? Well, there's a lot of hard-to-abate, expensive-to-abate emissions. Some with the energy sectors, such as airplanes, but there's also a lot in the agricultural sector. Use of fertilizers puts up a lot of N2O. So we're going to really need these offsets to take care of that to get to net zero. Estimates for how much we're going to need, they vary over a large range. If you look in the literature, people range anywhere from 2 gigatons a year to up to 20. What about going net negative? We see a lot about that. I feel going net negative is a big distraction at this point, talking about it. We can't even get to net negative till we get to net zero. That's not going to happen for at least a few decades, if not longer. And at that time, we'll know a lot more about the cost and the benefits of the different carbon dioxide removal technologies and can make informed opinions then about going net negative. In any case, to get to net zero, we're going to need carbon dioxide removal to operate at a gigaton scale. That's 1 billion tons a year or more. So, why do we need to do it now? These technologies take a long time to develop and scale up. And if we don't start now, they're not going to be available to us at mid-century. I'm going to focus now on direct air capture for the rest of my talk and on scaling that up. I wrote a book chapter that was published in a book last August on different carbon dioxide removal technologies. And I'll be happy to send anybody a copy of the chapter if they email me at hjherzog@mit.edu and just refer to this meeting here. So, how do we scale up? I'm going to talk about 3 steps. In step 1, you have to be brutally honest in assessing the challenges that you must overcome. I think Jan did a good start here talking about some of the challenges that Climeworks has faced. For direct air capture, a lot of these challenges come out of the fact that CO2 in the air around us is very, very dilute, 0.04%. That means you have to process a lot of air to get the CO2 out of it. This means you're going to have large equipment costs, large equipment sizes with large capital cost. It also means you're going to have significant energy requirements. And these energy requirements really have to be fulfilled by zero carbon or at least low carbon energy because as Jan told you, you don't want to emit CO2 while you're capturing CO2. It defeats the purpose, and you really only can take credit for the net amount of CO2 that you capture. And once again, you really need to operate 24/7 because you have expensive capital equipment sitting there. You don't want it idle, and it has to be in all sorts of weather. Step 2 is not to be fooled by simplistic analysis. And over the years, I read the literature, and there are several things that get me, let me say, a little agitated, and I'm going to give 3 examples. The first example is people say, well, we use air as a feed stream, therefore we can site a plant anywhere. Well, it is true that there's air everywhere, but that doesn't mean you can site the plant anywhere. Siting a plant is a complex process. It has many aspects to it. You have to look at land availability, access to energy and other utilities, the permitting issues, the meteorological conditions, accessibility of CO2 storage options, among other issues. The second example is people say, since there's unlimited feedstock of air, you're free to choose any capture fraction you want. So I can take out 10% or 90% of the CO2 out of a given volume of air. Well, that statement is absolutely true, and it's absolutely irrelevant. The capture fraction is determined by the design process. It's really a look at the trade-offs, the capital cost, operating cost, the operability of the plant, the reliability of the operations. Example 3, since we use thermal energy for regeneration in a lot of these plants, including the Climeworks plants, it can be supplied by waste heat. Once again, there's truth in this. There may be some opportunities to take advantage of this, but if you're going to be operating at a gigaton scale, those opportunities are only going to be a small fraction of the installations that you have out there. Step 3, just do it, because that's how you learn. So look at this as a journey. You're going to have certain requirements for the journey. First of all, you better have a good roadmap so you don't get lost. It's going to take a lot of hard work and determination, and it's going to take time and money. And it's probably going to take a lot more time and money than you anticipate at the beginning. Learning by doing is well proven in driving down cost. It improves it on many dimensions, the designs of the plant, the operation, the materials you use. It also is important in developing supply chains and understanding the permitting process and getting the reporting and verification systems down, among other things. Now, there is some good news on this journey. You may get help on the way. One thing we hope we're going to get help on here is the availability of low-cost, low-carbon energy. As our grids decarbonize, if we can decarbonize them and keep the price low, that is going to be very helpful. Then you don't have to go to places necessarily like Iceland to get this cheap, low-carbon energy. Also, other things are being developed, like small modular nuclear reactors, which I think could be a very good fit for direct air capture systems. A lot of work is going on today in the carbon capture community on developing storage hubs. And I want to correct in the introduction, I haven't been working on direct air capture for 30-odd years, but on carbon capture and storage is only recently that, well, I wouldn't say recently, I've been following it for 20 years and written a couple papers. But anyways, these storage hubs are an important part of the supply chain, and they can be developed outside of the direct air capture industry. You can take advantage of them. It gives you economies of scale for the storage of the CO2, and also broadens your geographic siting options. So I'm going to finish up here and come down to what I guess people always ask: what's the direct cost of direct air capture in the future? And I'm going to give you the definitive answer right now. Nobody really knows. There's a lot that's written. Numbers in the literature, you see a lot saying we're going to get $100 per ton of CO2. My analysis says, and the chapter I talks about it in quite a bit of detail, says I just don't believe that's a realistic or credible goal. And why is that important? Well, I think lowballing costs can result in a loss of credibility. And you really don't want to lose credibility, because if you lose your credibility, you're going to lose your access to the time and the money you need to scale up these processes. The good news is, though, that $100 per ton is not a magic number. What number does the direct air capture need to get to? Well, the answer is, what's the value of these negative emissions going to be in the future? And you just have to have a cost lower than that negative value to compete, value of these negative emissions to compete in the market. So I'm going to just finish and say, let's see where the journey takes us. Thank you.
Great, thanks, Howard, for sharing your insights and your very long-standing experience in the field. And I think the good thing is that you saw many other industries, so you haven't started with direct air capture, but you saw a lot of other technology maturing or not maturing in the field, and I think that's very important knowledge to dive into. So just want to follow up with a couple of questions. Let's first start with the timeline and the speed. So you said, hey, let's just go and start. And so when I talk to you, I sense a sense of urgency. You say, if by 2050 we want to be there, we really need to get things done. Other people, in particular from other industries, might think, well, that's a really long time, almost 30 years from now. Why do we need to start now if we want to be there 2050, or why can't we be there in 2030 or 2040? So what's your take on timelines when we talk about stuff like this, and why do we need to start now to be there in 2050?
So I've spent my career in the energy industry, and a lot of people look at sort of the electronics industry, things like cell phones, say, look how fast they came on and developed and the generations. But the amount of capital cost in a cell phone or other electronic devices is very small. When you're dealing with very high capital intensive industries, the timelines go a lot stronger. If we look at say some of the power industries, we have power plants operating today that have been over 50 years old. And so the generation time for turnover and for learning is hard. I can give you let me give you one example that I thought of. I went to the World Gas Conference in the mid-1990s, and at that point, BP's chairman was John Brown, and he gave a talk there, and he talked about LNG and how LNG was going to be like crude oil, tankers going all over the world, and this and that, and it was going to happen very fast. Well, that was, almost 30 years ago, and it's only recently that we start seeing his vision of the future starting to happen. And it still hasn't, hit the total scale yet, but it's starting to scale up thing. But that took 30 years, and, there's a lot of reasons for that. And partially it was some other innovations that needed to come in to make that happen. So I think you work on it, and there's going to be, I think, some innovations to come up because people are working on lots of different technologies that you can take advantage of, and you want to be primed when that comes to move forward.
Yeah, that makes total sense. I think those who are operating in the field, they feel it. Things take long, right? Until you build something, you learn from it, you can translate it into a next learning. That just takes time. We always speak about fast innovation cycles. Anything you can recommend to the players in those fields, how to become as fast as possible, even though it's an inert type of work you're working on?
Yeah, I mean, what people have talked about in the design industry, obviously using computers and simulation so you don't have to go out and build everything. And that helps, but it only could take you so far, as you found out in Iceland when you go out and really learn. I think what's going to happen is when you start going into other environments, there's going to be a whole new set of learning that you go there. So there's a lot you can anticipate, but there's always going to be things that you don't anticipate. In fact, projects I've seen is things that people anticipate, they do very well in getting it done. But then some simple things they don't anticipate, and it comes back to bite them. I remember a geothermal project, big geothermal project the United States government was doing about what they call today enhanced geothermal systems. And they're so worried about getting the underground right. That worked perfectly. But the special pump they got failed, and it failed because the seals were wrong. And that not only delayed the project, it also gave the Department of Energy a reason to cancel the project. So there's many components, and even the smallest thing can come in and cause you a lot of trouble.
Makes sense. I was speaking about harsh environments before, about hurricanes, snowstorms, sandstorms, all that stuff. I think to sum that up, we can speak about the necessity for robustness of designs. If you were to judge, if you had like 100% of your time and effort, money to spend, to what extent would you focus on robustness versus you would focus on efficiency, on performance upgrades of the system? So how important is this robustness really?
Well, I mean, robustness isn't sort of a sexy thing, because you know, it's like putting a new roof on your house. It doesn't, change it as opposed to putting a beautiful garden in front of your house. You don't get the acclimates, but without the robustness, it could be trouble. And the thing is, it depends. There's a whole range of things you need to be resilient for. Some are, one-time events that can happen, once in a while. Say you put something in Texas and you have a hurricane come. So if you don't protect against a hurricane, it could knock your whole plant out. But that may or may not harm you. It may take, it may not be this year or next year, maybe 20 years down the road. Other things are consistent, and if you don't do that, so say you're in an environment that you get a lot of, say you're out in the desert and you get a lot of sand coming in. Well, these, you use packing in these, in the plants, and if that packing gets, too much sand in there and don't need a lot to clog it up, I mean, that will just shut your plant down. So if you don't plan for that, so having the right type of, say, filters in your plant, then you're going to be in trouble. And so, these are, so I think it's critical, but once again, you just can't focus just on resiliency. You need to focus on everything. So, I don't know what the correct percentage is, but a lot of times people forget about resiliency because they just assume, the best operating conditions. They're in a rush to get out there. But if you do that, you're going to run into big trouble.
Makes sense. So let's talk about cost. Okay. You talked about cost. You gave your expectations. You didn't give a lot of detailed numbers, which makes a lot of sense. Nevertheless, let me challenge you with the same I stated there. So I said, when talking about cost, we should know exactly what we are talking about. So I said, hey, it's not only important to have your capital cost, your operational cost, but there is a lot of overheads. You need to know, are you talking cost per ton captured, cost per ton avoided, and so on. So what are the elements you have in mind, and what is most important?
When I talk about cost, I talk about all-in cost. And when you look in the literature at cost, sometimes they just talk about the cost of the capture. They don't talk about the cost of what we're going to do with the CO2 once we capture it. So you really need to talk about all-in cost. You need to talk about it on a net basis, net removed basis, not a gross removed basis. And I did give a number in my book chapter. I felt compelled to, so on that basis, I gave a number of between $600 and $1,000 per ton in the year 2030. I didn't want to look out further than that because we'll see how we progress then, and you can make the corrections. But I think that's still a fairly ambitious target. I saw your number, 400 to 700. We're not that far off in some ways, but I think it's still challenging. You and I were in a meeting in the Netherlands 2 months ago, and we had someone from Bechtel come in and say, well, since 2020, plant cost in general of these type of plants have gone up 30%, the capital cost of it. So, when we talk about numbers, not only do we have to talk about numbers, but what year numbers are those and how inflation will affect those also.
Yeah, I think there's one thing we can probably certainly agree to. If inflation carries on as it currently does, we will never see a value of $100 per ton in the actual year. So we can only speak about $2023. So that's clear. So for a final one, let's switch roles a little bit on your end. You've been for a long time the person in the field who has raised the warning voice and said, hey, we need to be brutally honest. We need to look at everything that can go wrong, and a lot of things will go wrong. So don't be over-optimistic because it'll lead us in the wrong direction. Now, I asked you for the last 2 minutes to switch sides. So let's think about what do you think needs to happen that we will end up in the very optimistic scenario? So what are things that could go better than we thought?
I mean, I think one thing, if you can get very cheap non-carbon energy, that would be helpful. And people say, oh, the energy cost isn't that big a part. But if you get cheap energy, there's also trade-offs between capital and energy. So if you get cheap energy, that will help reduce your capital cost, and it could be fairly significant. So I think that's number one. Second is a materials issue. These are big machines. Can we make them? They have to be hardened to the elements. So, are there going to be materials? Are there going to be ways that we can build these big machines with less, materials that are less expensive? So automobiles, they went from steel to aluminum and are still maintained all their safety. Are there things like we can learn from that that go into these machines? So I think those two things will be very important to do.
Which are other industries that you think this direct air capture industry can learn from, which can bring such innovation? So you mentioned automotive as one example, or the renewable energy industry.
I think, in a system like yours, you're going to need replication. So, so once again, solar, and I think solar is particularly benefited from replication of the solar cells themselves and getting those manufacturing costs down. And so I think, there are some examples you can learn from there. As I say, a lot of the heavy industries, the transportation industries, airplanes, cars, have gone to lightweight materials. I think you can learn from that. So those are a couple examples off the top of my head. I haven't thought about it that much, but.
Yeah. Super, thanks. Well, I recommend it to everyone to not only listen to what is said here, but also speak to those people who've been in the industry for years and decades and have seen that in the field. So I guess you'll have pretty busy breaks later on. So please make sure you take advantage of Howard being here and ask him all the other questions you have open there. Thank you, Howard.
Thank you. Thank you.